So thanks everyone for coming to the program. The speaker is Anna Newhart, and she is a ASP postdoc here in NCAR HAO, and she received her PhD last year from West University. And her main research interest is on ionosphere electrodynamics, ionosphere irregularities, and effects of magnetospheric convection. And today she will present results on the impact of prompt penetration of electric fields on plasma bubble growth rates. Go ahead.
Thanks so much. So yeah, what I'm talking about today is a little bit, it's one of my PhD projects, and then also what I've been working on, or continuing to work on for my ASP project as well. So be a little bit of a combination student. I guess it's great, you guys can see my virtual laser pointer. Okay, so the central question of my talk today is, how does storm time electrodynamics impact equatorial plasma bubble formation during major geomagnetic storms? So I'll start with just some background on the interaction between the ionosphere and the magnetosphere. Then I'll talk a little bit about equatorial plasma bubbles, since that's the ionospheric irregularity that I'm focusing on. Then I'll talk about the observations I use to look at the plasma bubbles, and then the numerical modeling that we use for comparison, and then the results themselves between the model data comparison and give a summary. So, okay. So during major geomagnetic storms, there are two major types of geomagnetic activity, those being prompt penetration electric fields, which are the direct result of the magnetospheric dynamo, and then ionospheric disturbance dynamo, which is primarily driven by high latitude energy input and heating in the thermosphere. So for this study, I'm focused primarily on the prompt penetration electric fields, which are a much shorter lived effect, since they're the result of the ring current failing to shield the ionosphere from the magnetospheric electric field. So they're going to happen very quickly. They're going to affect all latitudes pretty much at once, and are going to go away also pretty quickly, as opposed to the ionospheric disturbance dynamo, which takes much, much longer to set up, and then also takes much longer to go away. But even though I'm only focused, of course, on the PPEFs, in a real event, both are going to happen. So that's just something to keep in mind as we carry on. So equatorial plasma bubbles, I think many of you guys may be familiar, but for those of you who are not, I'll go through it a little bit. These are low-density plasma regions that form at sunset in a low-latitude ionosphere. They're large-scale structures, so on the order of tens to like 1,000 kilometers. And they're a really big source of interest in terms of ionospheric irregularities, because of the impact they can have on communication. Since EPBs, we have a low-density plasma region that you can actually cause GPS scintillation and also interrupt radio signals. So since this can interrupt communications, navigation, which are particularly important for agriculture, for scientific research, obviously people want to be able to understand what causes these and how we can predict them ultimately. So plasma bubbles can occur at any level of geomagnetic activity, but are more frequent during geomagnetic storms. And so I want to understand the role of geomagnetic activity so that ultimately, eventually, we can be able to predict their occurrence better. And so kind of the approach we're looking at here is that, is what conditions are going to contribute to equatorial plasma bubble formation? And kind of how we're looking at that is through the generalized Rayleigh-Taylor instability, since that is thought to be the underlying plasma phenomenon that causes equatorial plasma bubbles. And so here I just have a couple of examples of what equatorial plasma bubbles look like in different types of observations. So this is a plot from the Hippomarca and coherent scatter radar. So you can see that we have these big low density regions among much higher density regions. And so we don't really have a nice clean bubble. It's more what people talk about being like a flame type of shape. And so then this is an observation from the International Space Station, taking a density measurement flying through an equatorial plasma bubble. And I'll talk more about this later, since this is one of my sources for model data comparison. If you can imagine kind of a satellite flying through a structure sort of shaped like this, you can see how you can get a density structure, these big drops in density. So, okay, let's talk about the Rayleigh-Taylor instability. So the generalized Rayleigh-Taylor instability, so it's, it's the same as the fluid Rayleigh-Taylor instability. We have a high density plasma on top of a low density plasma and a perturbation between the two. Or I guess I should point here with the virtual laser pointer so that people can see too. And so this can occur in the equatorial ionosphere because of the ionospheric electric field configuration. And so that's because of the pre-reversal enhancement. That during the day, the E cross speed drifts in the equatorial ionosphere are upwards, as you can see here. So it's during the daytime in the middle here. And then at nighttime, they're downwards, they're negative. So at sunset, we need to transition between the two. And before turning to negative, we have an increase. It's called the pre-reversal enhancement. And it varies with season, as you can see here. That's kind of what this is starting to demonstrate. But the point is we have an increase in upward vertical drift because of E cross B electric field right before sunset, or right at sunset. And so the increased electric field causes the F layer to rise, which then at the same time the sun is setting. So we're losing our photoionization at lower altitudes, which sort of sets up the Rayleigh-Taylor instability since it gives us a steep gradient in plasma density. And since geomagnetic storms can produce large electric fields, this can strengthen this process, impacting the formation of or impacting the conditions that contribute to the Rayleigh-Taylor instability. Okay, so the Rayleigh-Taylor instability sort of has four stages. The first one being linear growth, and then kind of with increasing complexity all the way up to turbulent mixing. And in the F region ionosphere, we can have analytical growth rates of the instability for the first stage. So the typical way that this is approached is kind of with this paper from Peter Salton in 1996, which shows that, so he calculated the growth rates in the F region ionosphere. And in this case, this is a flex tube integrated setup. Since plasma does typically move in that way, that we kind of, so you're going to need global parameters in order to get the Rayleigh-Taylor growth rates. And you can see here that these depend on conductance, plasma velocity vertical to B, which is from zonal electric field, recombination, density, and then also the neutral wind and collision frequency. So in this formulation, the biggest driver of the instability is that density gradient. So that's the gravity-driven terms here. So as you can see, electric fields I've highlighted is also a direct contributor. But in general, this formulation is dominated by the gravity term, even during large geomagnetic events. But since then, there have been newer formulations that kind of better capture the contribution of electric field. So for this study, I'm using this formulation from Joe Huba that he published last year, in which case he added ion inertia and acceleration effects. And well, this formulation is typically only, like I said, it's a field line integration, but it's typically only integrated over the F region. But Joe added the E region as well. So he's doing the field line integration over a larger range of altitudes, in addition to adding ion inertia and acceleration effects. So during most conditions, ion inertia and acceleration don't actually make a big difference in this, like during quiet time. But during geomagnetic storms, it can make a really big difference. So we're better capturing those effects by including those here. The other thing is that by actually integrating over the E region, it better captures the effect of electric field on the Rayleigh-Taylor growth rates, which again, during quiet time wouldn't make that big of a difference, but obviously during a large geomagnetic storm, it can have a pretty dramatic effect. So that's why we're using this formulation as opposed to the Salton one, which is more commonly used. Okay, so in this case, I want to look at how the growth rates are affected by geomagnetic activity. And there have been a couple of previous studies that have looked at the growth rates in the ionosphere using other models. So there are a couple of previous studies on High GCM and Gaia and also on SAMI2. These are all primarily focused on climatology and to look at seasonal or tidal effects. But in this case, since I want to look at the effect of geomagnetic activity specifically, I'm doing an event study as opposed to longer term studies to look at climatological effects. Okay, so I've talked about the generalized Rayleigh-Taylor instability growth rates. Now I'll talk a little bit about the observations that I use to look at equatorial plasma bubbles. So I use data from the International Space Station's Floating Potential Measurement Unit. So it's just a Langmuir probe you can see here on the outside of the International Space Station. It was placed there to monitor spacecraft charging, but it can also measure electron density and temperature. ISS is at an altitude of about 400 kilometers, so generally well within the F region and well suited to look at equatorial plasma bubbles. ISS also has an orbital inclination of 51 degrees, so it spends more time at low latitude, giving you more opportunity to see something like plasma bubbles as an equatorial phenomenon. The major limitation with using this type of data set is the data coverage, since data is available on average maybe 1/2 to 1/3 of the time. And this is due to limitations with the downlink. Since this was originally placed to monitor spacecraft charging, not necessarily as a science instrument. So it has to share the downlink with other instruments and doesn't always get it. The other issue is because of the way the downlink from the International Space Station works, there are certain longitudes that are never covered. But this is kind of an underutilized data set. It is publicly available on CDA Web, though, if you're interested in taking a look at it. But okay, so yeah, this is what we used to look at this. We also compared this, I'm not going to show the results here, but we did also look at swarm and DMST for these time periods. So those kind of used in conjunction are particularly valuable. So the time period that I am going to focus on for today is the September 2017 geomagnetic storm. We chose this time period just since it's a major geomagnetic storm, and until a couple weeks ago, it was the most recent major geomagnetic storm. And it's a double main phase. It began on the 8th of September 2017, or the first main phase did. And in this case, it's just good for looking at plasma bubbles because many plasma bubbles and unusual features were observed. Just the sheer size of the disturbance makes it a good option. The other thing that makes this time period advantageous is the availability of the Hickamarca incoherent scatter radar drift velocity observations. So in this case, we actually have equatorial electric field observations to compare to our modeling results, which is very valuable. So Hickamarca, for those of you who may not be familiar, Hickamarca is in Peru, right at the geomagnetic equator. And so because of the timing of the main phase of the storm, Hickamarca was right at dusk when the main phase of the storm began. So you can see here that this is local time at Hickamarca, and then the upward drifts that were observed. The green is the climatology, so we would typically expect that like pre-reversal enhancement. And then the blue are the actual observations. And rather than just a small pre-reversal enhancement, what we got was a really strong prompt penetration electric field, causing a really strong vertical uplift. And so these are the kind of conditions where we would expect to form large equatorial plasma bubbles, since it would block the ionosphere so dramatically. Okay, and so now, and if you're interested, because there's more information about this in here from Bella Fair from a couple years ago. So now I'm going to talk a little bit about a couple examples of equatorial plasma bubbles observed by the Floating Potential Measurement Unit on ISS. And so in this case, what I'm defining to be an equatorial plasma bubble are fluctuations in density of greater than an order of magnitude. So these are just a couple of examples, and I'll go through all of them in a little bit more detail. So my first example here is right from the beginning of the main phase of the storm at about 2:30 UT on the 8th. And so in this case, we have magnetic latitude plotted against density observed by ISS. Then I also have a total electron content interpolated along ISS's trajectory. In this case, just for sort of comparison purposes. And we can see that we would typically expect to see just plasma bubbles kind of confined to the equatorial region. But in this case, the bubble is so large that it is actually extending all the way down to mid-latitude in the southern hemisphere. And so this was occurring over the American sector. So the same kind of general area where Hickamarca is located. And also in this case, even though I just plotted total electron content sort of for general density comparison, and I wouldn't actually expect to see a plasma bubble in at least this form of total electron content, just because it is so coarse-grained. But in this case, the plasma bubble is so large that you see it in total electron content as well. So this is a really dramatic example, to the point that ISS observed it in multiple subsequent orbits, and that it was kind of a whole region of bubbles. So it may have been multiple plasma bubbles that all formed together. Okay, and so now just to contrast that really dramatic example, I have a much less dramatic example from the recovery phase of the storm. And so in this case, we have small dips in density of about an order of magnitude, sort of confined to right around the magnetic equator. And this was during the recovery phase of the storm on the 9th of September. So this is maybe more in line with what we might typically see in terms of plasma bubble observations, as opposed to the really dramatic example I just showed a minute ago. Okay, so in total, ISS observed 13 of these EPV or depletion type irregularities during the geomagnetic storm, which that represents a significant fraction of the total number of orbits that ISS had during that time period. And these occurred primarily during the main phase of the storm. So the period of largest disturbance, which is when we would expect this is when we would typically expect to see these types of events. So one thing to keep in mind here is that ISS is its local time shifts over the course of about a year, but during this time period, it was crossing the equator right around midnight. So the bubbles may have actually been forming at slightly earlier or possibly slightly later local times, but ISS is only confined to be able to see them in that particular window, just since that's what's in that region. Okay, so now we want to take these plasma bubble observations and compare them to our generalized Rayleigh-Taylor instability growth rates. And in order to do that, since we need global parameters, we're going to need to do some type of numerical modeling. So in this case, we use SAMI3 RCM. So this is an intermagnetosphere model coupled to a ionosphere model. And so RCM is the Rice convection model. It's a bounce average drift kinetic model describing the intermagnetosphere and its interaction with the ionosphere. And so this is the sort of schematic showing the way RCM works. RCM is iteratively solving the Vassal-Linus equation. So it starts with an initial plasma distribution and boundary condition. Using that to get this magnetospheric particle distribution. From that, it can calculate the gradient and drift currents, and then the field and line currents. And then with a bunch of ionospheric inputs, it can calculate ionospheric electric field. And so if RCM was running on its own, these would typically be empirical models it was using. But in this case, since it's coupled to SAMI3, SAMI3 is giving some of these inputs. So for my ionospheric electric field, we can map that back out to the magnetosphere, give magnetospheric electric field, step our particle distribution forward in time, and we're back to magnetospheric particle distribution. And so in this case, what's really important is that since RCM is solving for these electric fields, RCM is very, very effective at modeling prompt penetration electric fields. So since it's modeling that ring current distribution and whether or not it's able to shield the ionosphere. So it gives ionospheric electric field for our Rayleigh-Taylor instability calculation. So SAMI3 is a first principles ionosphere model, modeling the ionosphere from about 85 kilometers all the way up into the plasmasphere, giving both the dynamic and chemical evolution in the ionosphere. And so in this case, what's important is that it calculates ionospheric density and ionospheric conductance, both of which we need for it to do the Rayleigh-Taylor instability calculation. RCM and SAMI3 are fully two-way coupled via the potential equation. SAMI3 is providing the conductance tensor to RCM. RCM is solving for potential and then providing that and electric field to SAMI3. Both SAMI3 and RCM are using electric field to step forward in time and change their plasma distribution. But the major limitation here with this setup is that the neutral wind dynamo is fixed at 5 time level, so it's using MSIS. So this means that we can't make plasma bubbles directly in the model, since we would need a neutral atmosphere in order to do so. So something like WACOMX or something like that, which is why then we use the growth rates rather than forming plasma bubbles directly in the model. It also means we can't capture any ionosphere disturbance dynamo effects, only prompt penetration electric fields. Okay, so here are some of the electric field results. So these are the magnetospheric contribution from the electric field from RCM, and in 4 different sectors of magnetic longitude. So since these are magnetic longitude, this would roughly correspond to Hickomarca's location, and then kind of stepping forward all the way around the globe. And so we can see during the initial phase of the storm, pretty much all locations show some level of disturbance. And then this becomes much more dramatic as we enter the first and then second main phases of the storm. So we're seeing global electrodynamic disturbance as the result of the September 2017 storm, although the timing and magnitude depend on the local time at the time of the disturbance. And so just for a rough comparison, so these are my model results from RCM. And just for a rough comparison, I'm going to plot the location of the plasma bubbles. Obviously, I only have 4 sectors of longitude, so this is a very rough comparison. But just to show the timing and kind of the sector where they occurred. And so we can see that we have a few plasma bubbles occurring during the initial phase of the storm, kind of in response to that first electrodynamic disturbance. But most of the plasma bubbles are occurring during the main phase of the storm, and preferentially in the American sector, which that's where we saw that really big plasma bubble example that I showed earlier. And then, of course, there are a few examples continuing afterwards as the ionosphere recovers and returns to its quiet state. Okay, so now to look at this more in depth, we can look at the Rayleigh-Taylor instability growth rates themselves. So these are the maximum, this is a plot from Joe Huba of the maximum GRTI growth rate from any apex altitude as a function of local time and UT during the September 2017 storm. So we have local time on the y-axis, and then this is UT or model time on the y-axis, and then this is just the DST storm for comparison. And so this is the formulation, like I said earlier, using both the E and F region drivers to make sure we're fully capturing the effect of the electric field. On September 6th, on the quiet day before the storm began, we do see enhanced growth rates kind of right around dusk, which is what we would typically expect to see for the Rayleigh-Taylor instability. Though by including F region or E region drivers, we also do see some enhancements kind of post-midnight as well, even at quiet time. On September 7th, during the initial phase of the storm, we see some enhancement around dusk, but the more dramatic enhancement is actually post-midnight. And then during the first main phase of the storm on September 8th, we see the growth rates are increased significantly, both post-midnight, but the biggest difference, or pre-midnight at dusk, but the biggest difference is here post-midnight, where we see these really dramatic examples. And then you can see the same thing in the second main phase of the storm, although SAMI3 ingests daily indices, so this discontinuity here is not physical, that's a result of it taking daily indices. But we can still see that the ionosphere, then after the main phase of the storm ends, it sort of returns to the quiet time setup, although the dusk growth rates do remain enhanced. And so this shows very good agreement with the plasma bubble occurrence that we saw from ISS. That most plasma bubbles are occurring during the main phase of the storm, which is when we're seeing the highest growth rates. And that during the main phase of the storm, the plasma bubbles are occurring in a larger range of local times. So as opposed to just occurring here at dusk, we're seeing them occurring post-midnight as well, which is where we're seeing these really large growth rates. So now we can look at the plasma bubbles, or the GRTI growth rates as a function of altitude to look at them in greater detail. So this is the quiet time sort of setup. So this is from before the storm began, right at the end of, or the end of the quiet day before the storm started, right before the initial phase of the storm. And so as I said before, we can see the enhancement right around dusk here. But interestingly, when we include the E region drivers, we do actually see some enhancement post-midnight as well, and this enhancement up here at higher altitudes. But when we consider kind of where ISS is flying through, that's at 400 kilometers here, there aren't, we don't see any significant enhancement. And in many cases, the plasma bubble, or the growth rates are actually zero at ISS's altitude. And so this is in good agreement with the observations from ISS, since no plasma bubbles were observed during this time period. And so now to compare this with our electric field results from the same time period. So these are, this is field line integrated electric field at the same time. And oh, well, on this screen, you can't really see it at all. But that actually in some ways illustrates the point. There's no significant electric field enhancement here. On my screen, you can see something, but suffice to say that it's all nearly zero. We have a small enhancement here, which is just the typical quiet time pre-reversal enhancement, and then you can see everything goes negative at night, as we'd expect to see. So that's sort of driving this sort of small enhancement here, but this is sort of the typical quiet time configuration. Okay, so now when we get into the main phase of the storm, we see that the growth rate structure changes significantly. The growth rates around dusk have increased by a lot, and they've extended to higher altitudes. And then we have the enhancement post-midnight, where the same thing is happening, only the enhancement is much stronger. So now if we think about where ISS would fly through at 400 kilometers, we're flying through regions that have, positive and in fact significantly enhanced growth rates. So we would expect plasma bubbles to be forming in the region where ISS would be flying through. And now if we compare this to the electric field from the same thing. See, okay, now you can see it on this photo. That's good. Okay. So now we can see in the same region where we're seeing this huge enhancement in the growth rates, we have these, we have really strong electric field in this post-midnight region. So we can, so in this case, it's pretty clear to see how these strong upward drifts are contributing to this large enhancement in GRTI growth rate here, both at ISS's altitude and above. So this does raise the question, if we're having significant, if we're having a strong electric field, which would lock the F region, and we can see the growth rates are very high, well above where we would typically expect them to see, or expect them to be. Whether or not that what ISS is observing at these time periods are actually equatorial plasma bubbles, since they're only making observation in a single orbit. And if you have the F region just go above ISS, it's going to look like you saw a plasma bubble, since when really what you just went was below the F region. And so I looked into this a little bit with the HMF2 results from SAMI-3. And while I cannot completely rule that out as a possibility for some of the equatorial plasma bubble observations, it looks like the increase in HMF2 was pretty much kind of confined to right along the equator. And so most of the plasma bubble observations go off the equator to some degree, and which means that they cannot be fully explained just by lofting up the F region, meaning they're probably at least in part real plasma bubbles. But again, this has good agreement with our plasma bubble observations, since we're seeing more and more plasma bubbles at later local times, and we're seeing really large, really intense examples of plasma bubbles, as opposed to the smaller examples we saw during the initial phase of the storm. Okay, so far, we've seen pretty good agreement, but there is an important issue here with these results, which is that when we make a direct comparison between the electric field results from the model and the electric field results from Hickamarka, there's large disagreement. So this is a plot of Hickamarka drifts and the RCM results from the September storm. And so the RCM results are the yellow, and the Hickamarka results are the blue. So right at the beginning of the main phase of the storm, when we had that large prompt penetration electric field that I discussed earlier, observed by Hickamarka, RCM actually does not show a prompt penetration electric field. It shows a negative reaction in vertical drift. So even though it's getting the timing correct, it's not matching the sign of the initial uplift. It's obviously a really big issue. If I want to look at the effect of prompt penetration electric fields, I would really like for my model to create prompt penetration electric fields. But there's quite a few explanations as to why this would happen using SAMI-3 RCM. The biggest one being that if we're only using RCM, we can only get phenomena that occur in the inner magnetosphere. Anything that's happening out in the magnetotail, or effects from the sudden storm commencement from the compression of the magnetopause, are not going to be able to be reflected in RCM, just simply because it doesn't create that type of physics. And so there's been a study last year from Bella Fair and Luis Navarro, where they showed that they believe that these prompt penetration electric fields for Hickamarka were almost entirely driven by substorm effects. And so in this case, what they're plotting are the drifts from Hickamarka during the September storm. In this case, they're showing both the upward and eastward drifts. And then the each arrow here is substorm onset. And so they are associating kind of the changes in the drifts with those substorm onsets. And their argument is that these are driven almost entirely by substorms. If this is the case, this is obviously a problem, since RCM has no ability to model substorms. But what I'm working on now is to use MAGE to look at this event. So since MAGE incorporates Gamera for a global magnetosphere, and then RCM along with a remix for the electrodynamics to get the inner magnetosphere, and then TiGCM for the ionosphere and thermosphere, it has a much better chance of being able to capture these type of dynamics. And so this is still very much an area that I'm working on. This is just from a few weeks ago. This is the same time period, but using MAGE And we see that, that MAGE does create at least that initial PPEDS, although it has a smaller amplitude than what HAO initially observed. So this is at least promising that even if we're not getting like a perfect one-to-one match here, that HAO or that MAGE is at least to get the general effect. So this is something I'm continuing to research and investigate. Okay, so and in terms of future work, in addition, like I just talked about, I want to look more into storm time electrodynamics using MAGE in hopes of being able to capture the effect of substorms and other effects that are not possible using only SAMI3 and RCM. I'm also really interested in looking at neutral wind effects using WACAMX along with SAMI3 and RCM, because this is an example from Joe Huba where they were using WACAMX coupled to SAMI3, and they can actually make the bubbles directly in the model. Since, of course, in addition to storm time electric fields, changes in the neutral atmosphere will also have a big effect on plasma bubble creation. And okay, well, I guess I'll just leave you guys with my summary, and which is that ISS observed 13 of these equatorial plasma bubbles during the September 2017 storm. Most of these occurred during prompt penetration electric field events, but the prompt penetration electric field results from the model do not show good agreement with HAO measurements, at least when using SAMI3 RCM. But overall, growth rates that include E-region drivers still do show good agreement with the plasma bubble occurrence. So even though overall we're capturing kind of the general dynamics that contribute to EPB formation, we're not necessarily capturing the details of the electrodynamics. But thank you.
Are there any questions, either in person or online? I'm not sure who is first, but Mary or Bill, one of you want to go ahead?
Mary, why don't you go ahead?
Okay. All right. Okay. This is really nice work, Anna, and I go back. My interest in equatorial plasma bubbles goes back to my PhD thesis, which was many decades ago. I have been interested in this storm. My group has studied it using LFM-RCM. It's a very complicated storm, multiple CMEs impacting the magnetosphere. It wasn't just a single clean hit. So my understanding the last time I heard Slava give a presentation on this was that Gamera was having some difficulties reproducing things like the double dip ring current and features like that of the storm, Gamera coupled to RCM. And so I just haven't heard an update on how things are going with that. But I heard him give a presentation just addressing the challenges of simulating a storm that involves multiple CME encounter with the magnetosphere in a very short period of time. Any comment on that?
I mean, I guess you make a very good point that these large dramatic events. I mean, I've heard Slava talk a little bit about that, and I know that Kevin was cautioning me because he's saying it's an O+ event, which also complicates it as well. So I guess I'm definitely going to work more on it. We'll see how it goes.
I guess my suggestion would be that there are other interesting storms beginning to occur, and that did occur prior to September, early September 2017, that are less complicated. And so and with this good database from space station, you might also in the course of your studies look at a less complicated event. It's sort of like Whippy looking at solar minimum,
Right.
Instead of maximum. Yeah.
That makes sense.
Bill, do you want to go ahead?
Yeah, so Anastasia, could you go back to slide 31, please? I guess it's this one. And Mary's question and comments may have already provided some partial answers to my question, but so while the increase of the upward drift from MAGE is doing a reasonable job in the vicinity of the red box that you showed there, it also has what looks to be like significant upward drifts later that don't seem to be observed,
Yes.
by Hickabarka and so on. And so maybe the answer is that it's this complicated storm that Mary was talking about, but if you have any insights into why that's occurring, do you have any?
Well, part of it is there's a detail point that I should have made a little more clearly here, which is I've subtracted out the background from this and I did not do it to this one. So even though the largest contribution here would be from storm time electric field, this also does have the ionospheric diurnal variation from it in it as well. So that's a small portion of the difference. But one issue that I've heard is that Gamera, so if these really are substorm driven, that Gamera may actually be overshooting on that. Showing too much substorm contribution. So that's another possibility, but I'm still working on it.
Well, I think it's exciting that you're working with, a global model that has the capacity potentially to produce equatorial bubbles. So it looks very interesting, and I guess we'll keep our ears tuned for more in the future. Thank you.
Thank you. Yeah. No, I was so thrilled when I made this plot. I remember I showed it to a couple other people and they're like, I mean, that seems okay. And I was like, no, let me show you this plot first. And then you'll see that this plot is very good.
Any other questions?
So how does the penetration electric field be generated in range?
In terms of like this, how you in terms of substorm driven ones or just in general?
Just general penetration electric field.
So it would be MAGE has RCM in it.
Okay.
So it would be that portion would be the same. Just that MAGE with using Remix can looks at all the other current systems in the magnetosphere as well. So it can also capture those magnetotail contributions too. But I mean, since RCM itself is in there, like that part's the same.
Is that a major on the Gamera RCM run? The bottom plot.
I think so. This is one of Chan's ones.
Okay. So to answer your question, and now also the cover that just as the magnetosphere inputs get the highlighted convection. The convection when combined with IGCM or other IT models can have the effects through the boundary condition.
Still set the boundary condition.
Yeah.
Okay. I see.
So there was a question in the chat I can read. So Amadi Brian said, thanks for a nice presentation. Since the shielding electric field may have recovered during the main phase and can also penetrate to low latitude ionosphere, and some studies have also observed the presence of eastward oriented disturbance electric field. How did you confirm that the development of the plasma bubbles and E cross B drift is actually due to prompt penetration of electric field and not that other fields?
Oh, well, that's the limitation of using SAM-3 RCM. SAM-3 RCM can only make prompt penetration electric fields, can't make other types of electric fields. So in that case, I'm only looking at that specific contribution. Though of course, in a real event, you will create an ionospheric disturbance dynamo as well.
So in the MAGE simulation, I guess you get both.
Yes. Yeah.
Other questions, either in the room or online?
Yeah, I think I don't understand what's that the red dots there.
Oh, those are the spread F flags. So they just sort of indicate poor data quality.
Poor data quality.
Yeah. In this case, this is from data is from Luis Navarro that they had sort of averaged over a larger range of altitudes than they typically do with the market data in order to recover the drift measurements from the spread F. So it's like, normally you'd have very good resolution, but I think that for these, they were averaging over like 200 to 900 or something like that.
Also, you mentioned the top plot has the background subtracted. How is that background determined? Do you see that?
I don't remember. There's a it's a climatology that Luis sent me. So I guess I don't remember the exact method he
Just
used to
a
do it.
long-term background.
Yeah, they have just a long-term form that they use to subtract off. Because you can still it's not a super good way to do it because you can still kind of see it here. Like it's not a very effective way, but it's better than nothing to at least be able to, since RCM obviously is only going to have magnetospheric. So to do a one-to-one comparison, you have to subtract something off.
But that's just for the data side. The RCM results is just whatever you got from the model.
Yeah, because RCM doesn't have ionospheric electric fields in it. So you can just plot it on its own.
I have another question. Yeah, because earlier you mentioned that I think just for this event, you said the bubble is so strong that even the TC shows some response to the depletion. So just generally speaking, in altitude range, how large is the bubble in the typical case?
I guess you can see that better in the radar measurements because obviously ISS is just stuck at one altitude. But like here in the radar, you can sort of see them like maybe starting down in the lower parts of the ionosphere, but sort of kind of continuing up as well, up to like 800 kilometers.
Well, my eyes are not really.
Okay,
So which part is the bubble on this plot?
I think it's sort of the low densities, like the holes.
Like this black area?
The white area.
Okay.
The white area. So you can have them forming all the way down in the lower parts of the F region. But then once they form, they rise upward. And then I think they typically maybe rise up to say 800 kilometers and then just sort of hang out there and then eventually dissipate. But that's sort of, ISS is just sort of stuck at the one place. So if you're making them up here, that's too bad. Can't see that with the satellite.
So basically like vertically, the bubble can still occupy a very large portion of the entire ionosphere. So,
I believe so. I'm not sure I guess I haven't looked specifically at the like vertical extent of them because people usually talk about their length.
Yeah.
And then they move upwards over time. Because I know that they're able to occupy a very large range of altitudes, but
So in relation to that, if you look at the the last slide.
oh
the
yeah.
SEMI Animation or simulation, is that pretty realistic that depletion depth?
Like these.
Yeah.
I mean, I think it's not my area of expertise, but I think so.
I don't know if those are fully formed.
They are still developing.
Yeah.
That's a good point. Yeah, I would go back through.
For quite that much. That's don't have it.
So the deeper.
Right.
Yeah, because I mean this, if I go again, if these are showing like kind of a few hundred kilometers here, but I think this is like a very, very dramatic example because this is, a cool picture everyone shows. So
I think sometimes they can see them in DMSP observation, which is 800
Oh, yeah.
kilometer.
they survived that high.
Also, lastly, I just want to point out even the SEMI and the Ionosphere, that's also in the general MAGE model. So right now we refer to MAGE, you're referring to the special Gamera RCM. But generally speaking, the MAGE diagram includes
yes.
RCM and the Ionosphere.
Yeah, that's a good point. That's a good point. I always forget that note. This is not that. I will specify next time.
That's a simple question. So you said the prompt penetration is short, it's fast, and then the other disturbance is long. How short and how long? What's the time scales?
So prompt penetration electric fields are usually hours. So the exact timing, like how long you can sustain one is like an area of debate.
Oh.
But like a few hours, I think is typically like the maximum. But like the atmosphere disturbance dynamo, I think you could set up for days, in the right conditions.
So I remember the penetration can also be very long lasting. Like the Transform has paper reporting a long-lasting penetration. That's like even on 1 day or even more than that.
Okay. That's quite unusual though.
Right on Europe. Right?
Any final questions? Thank you again.